Hi guys, can you give me a sound check?
Sound
I
good?
can hear you.
Yes, sir.
Thank you. Cool. Okay, guys. So let's see. Before we get started, is there any housekeeping stuff? If you guys are, I know some of you guys are having a hard time adding the class, and you know, I'll just keep pinging me, letting me know. I can reach out to Margell, etc. But unfortunately, I'm not like a full-time faculty member, and I don't really know the rules too well. So I'm kind of guessing as how to get you guys on as much as you guys may be. But anyway, keep me in the loop. I'll try to do what I can to help. I know, and I think there's 3 or 4 of you guys having a hard time adding. Can you guys maybe at the end of the class shoot me an email if you're still having a problem? Appreciate it. Thanks. Any other questions before we get started? Okay, so let's see where we left off on Tuesday, I think, was this slide where we were talking about the free carrier density. So we talked about semiconductors or like a conductor that sometimes conducts, that sometimes is, you know, pretty much anytime there's some kind of a temperature, certainly in room temperature, it's conducting. But how many, you know, electrons are available depends on its band gap and depends on the temperature. And you know, this top equation here, Ni, this equation shows you guys that, you know, there's a sort of a strongish function of temperature, and, you know, there's other physical constants involved. And the thing to remember from this one is this is kind of a good number to remember, or at least know where to look up, which is the density of carriers at 300 degrees Kelvin, which is room temperature, at and it's 1.08 times 10th electrons per centimeter cubed. Okay. And the other thing to take away from this is as temperature increases, the carrier density goes up, and it goes up significantly. Okay, so again, I just saw like 5 orders of magnitude here. Well, it's 300 degrees is a lot of temperature difference, but you know, temperature went up by, I guess, a factor of 2. The carrier density went up by 5 orders of magnitude. Okay, so next. So, you know, we talked about you can use, so by definition also, the other thing we talked about was that by definition, let's say you have just a plain, pure silicon material. For every electron that gets created, so for every electron here, there's a hole created or a lack of electron created. So there's exactly the same number of electrons and holes, okay? So let's say we want to increase the relative number of electrons compared to holes. how do we do that? And it'll become obvious why we're trying to do it once we get into the PN junctions and diodes. But for the sake of discussion right now, let's just say we want to increase the number of electrons. We said that what you could do is to go to a column 5 in the periodic table, and both phosphorus and arsenic are popular dopants for this. And basically you can add that to your silicon, and because phosphorus or any of these group 5 elements have 5 valence electrons compared to silicon's 4 valence electrons, there's always a spare valence electron that's floating around. So for every phosphorus atom that you inject into the silicon matrix, you'll actually have a spare electron for which there is no corresponding hole. Okay, so the way people actually do this is, let's say you have a silicon crystal or silicon wafer. You guys may have seen silicon wafers that they make semiconductor chips from. They actually have these expensive machines called ion implanters, which are basically, you can think of them as ion cannons. So basically they get phosphorus ions and just slam them into this the surface of silicon. These things, just like a cannonball, they'll just ram right through your crystal and lodge themselves at some point in this crystal lattice. And so now you have these spare electrons. Okay, now of course, on the other side, if you want an excess number of holes, what you can do is to go to get some stuff from group 3, and their boron is the popular choice, and use that to dope the silicon. And what you get, because a boron or any group 3 dopant has only 3 valence electrons, you'll always have a hole for which there is no corresponding electron. Okay, so that way you can make a piece of semiconductor have excess holes or excess electrons. Now, one of the things to remember is the number of excess holes or excess electrons when you implant. The density of, say, boron atoms compared to the silicon atoms in a lattice is actually pretty low. Like, let's say, the silicon, let's say we have for a, let's, I think I'm jumping the gun here. Let's talk about this in a little bit. Okay, so here's the summary. We have electrons and holes, and then we can have, we can dope the silicon with either acceptors, which are group 3 dopants, or donors. So that's acceptors here. Oops. Acceptors, or donors, which are group 5 dopants, to either get extra holes or extra electrons. Do you guys have any questions about anything so far? I remember I had kind of a problem with the idea of holes initially, but I think you just think of it as, from a physics standpoint, I guess you can think of it as an absence of an electron. But after that, I would just think of it as as if you had a positively charged particle, which you don't, but you can, from a circuit point of view, when we're calculating currents, etc., just think of it as a positively charged particle in the way it reacts to an electric field. So that's pretty much how I look at holes, sort of from a circuit standpoint or a device standpoint. Any questions?
Professor?
Yeah.
You said that the group 5s are acceptors or donors?
Group 5 are donors.
All right.
Because group 5, they have an excess electron. So they have 5 valence electrons. So they they donate an extra electron into the lattice. I don't know why they call it donors. Sort of convention.
All right, thank you.
Sure. Okay, so next, moving on. And so I'm kind of, you guys have got to bear with me for a little bit. I'm just giving you some background stuff. Again, we're moving towards a PN junction. What happens when you get a PN junction and you get a diode, et cetera. So this is just background stuff you need to know. The other thing you need to know, and this we are presenting as a given in this class, but you know, there's a proof for it in semiconductor book stuff. But for now, just take it as a given that the product of electron and hole pairs, oops, the product of electrons and holes densities is always equal to the square of the intrinsic electron density. Okay, regardless of the doping level. So this is always true. Okay, so you just got to take that as the word of God as far as this class is concerned. So let's see, what does that mean if you have a piece of silicon that has it's an N-type. So N-type means that it has excess donors, means it has, you know, phosphorus or something like that. Phosphorus, I'm probably misspelling phosphorus. That's been dumped on there, and so it has, the phosphorus is doped or is implanted in there at some density, N sub D. Okay, oops, sorry guys. So let's say this is the case. Okay, if this is the case, the number of, so if you have this N-type material, N-type material is a piece of semiconductor that has donors or implanted in there. These are just sort of definitions. So we call that N-type. So let's say you have an N-type material, then the electrons, because you have an excess of electrons, you call the electrons the majority carriers. These are all just definitions. But you'll see why it's called. So N in this case is majority carrier. Okay, I'm gonna put in a P-type material here. So if you have a P-type material, you've doped this with acceptors, say for example boron, and you say N sub A is the density of boron implant per centimeter cubed. And in this case, holes are the majority carriers. So N-type silicon and electrons are majority carriers. P-type silicon, holes are majority carriers. Any questions about that? Okay, so here, because N sub D is, if assuming N sub D, we dope this silicon, but this is an assumption, much higher than N sub I. Okay, let's say we just dope the heck out of this material. Okay, much higher than, let's say, so N sub I, we said at room temperature is 1.08 times 10 to the 10th per cubic centimeter. Okay, that we had from here. Sorry about my dog, guys. It just keeps chiming in, saying hi to the neighbors. Okay, so let's say this is the n sub I is 1.08. Let's say n sub D, we make that, typical numbers you'll see is 1 times 10 to the, say, 15 or 16 per cubic centimeter. That's up to us, the manufacturer, whatever, to dope it as much as we want. So if you do this, then the majority carriers, the N is approximately N sub D. Okay, so the majority carriers end up being the doping concentration. Okay, so the doping concentration, the nice thing about that is we know the doping concentration because the manufacturer or ourselves, we doped it a certain way. So we know what the majority carrier concentration is in that piece of N silicon. And then because we have this magic equation, we know that N times P is Ni squared always. So if N is N sub D, P is equal to Ni squared over N sub D. Okay, because in this case, if N is equal to N sub D. Okay, so the nice thing there, we know the donor concentration, we doped it, so we know both the majority concentration and the minority carrier concentration. Any questions about that?
No.
And then, so let's say in this case, I mean, I'm not gonna run the numbers, but as you can see, if, Ni was one, let's say we take this case, right? Ni was 1.08 times 10 to the 10th. So Ni squared is roughly, I don't know, is 1 times 10 to the 20th, like approximately, right? So if 1 times 10 to the 20th over 1 times 10 to the 16th, so P is roughly 1 times 10 to the 4th. Okay, so in an N-type silicon, now we know why P is called minority carrier in an N-type silicon and N is called majority carrier, because you can see the excess electrons or the free electrons are, their concentration is around 1 times 10 to the 16th per centimeter cube in this case, and the holes are 1 times 10 to the 4th per centimeter cube. So you have much, much, much less holes than you do electrons in an N-type material. Of course, it depends on the doping levels, but this is how the typical doping levels that you'll see for PN junctions, again, the device that we're interested in. And we can run the same type of ideas here for P-type material. Again, we've doped it a certain way. If the number of acceptor dopants is much higher than Ni, then the whole carrier concentration will be almost the same as the acceptor concentration, and that'll be the majority carriers. Oops. And the free electron concentration is Ni squared over N sub A. Okay, that's a minority carrier concentration. Sorry about my handwriting, guys. So they're just, N-type material, majority carriers of electrons, minority carriers are holes. P-type material, majority carriers are holes, minority carriers are electrons. Okay. Any questions about that? So this is an important thing to remember. Okay, that everything I just said. So in a P-type material, majority carrier are holes. They're equal to the acceptor concentration that we've doped the material with. And you can find the minority carriers in that case, which are the electrons, by dividing by the Ni squared, the free carrier density, by that acceptor concentration, and vice versa for the donors. Now, the tricky thing to remember here, so, let's say you're given this in a problem, right? You're given the acceptor carrier concentration. Regardless of what happens, the number of holes is that. But remember that because Ni squared, or say Ni, is a function of temperature, the minority carrier concentration, the electron carrier concentration, will actually be a function of temperature. It'll go up and down with temperature as Ni changes with temperature. So when it comes to the problems, make sure you're using the Ni, the correct Ni for the temperature that the problem specifies, okay? Okay, let's keep going then. Okay, so we got all our bookkeeping. Now we're gonna talk about currents. So remember that we talked about a conductor, the way current gets conducted through a conductor is you put an electric field across your conductors, across your wire, put an electric field across it, and you have electrons and they flow from the, electrons are negatively charged. So they're, going from the positive, they're getting pushed from the positive plate towards the the negative plate or negative voltage, okay? And then the electric field is the change in voltage with respect to distance, the negative of that, okay? So that, I'm hoping you guys remember these equations. So basically by putting an electric potential across a conductor, you've put an electric field across the conductor, and that electric field is pushing those electrons in a certain direction. Okay, so in a semiconductor, you have that type of current transportation, but you also have a second type of current transport. But let's talk about this. So which is the same thing as conductors, as semiconductors. And this is called drift, because the electrons or carriers are drifting along with the electric field. That's why they're called that. And so what happens though, and this just kind of happens in a conductor too, but certainly in a semiconductor, is say this is silicon, right? A silicon crystal, if you think of this thing as a silicon crystal, is full of atoms. And so what happens is the electrons don't go shooting across. I guess the electrons would be going in this direction if the electric field's in this direction. Don't go shooting across like they would in a vacuum. But what happens is they go a certain distance. After a while, they hit an atom and get deflected, and maybe go a certain direction, certain distance, get deflected again, so on. But in general, they drift along in the opposite direction of the electric field. So the general motion is in this direction. But if you look at an individual electron or individual carrier, it'll just be sort of bouncing around. So what they've come up with is this thing called mobility, which is this mu sub p, that basically defines how many, how much you get slowed down, let's say. So basically the velocity of holes or electrons in a semiconductor, or
Let's start recording as well, right?
It still says recording for the iPad at the top left, so I think we're good.
I think it's connected to another device.
Yeah, I just saw his name pop up.
Yeah, hi guys.
No.
Sorry, I my internet. Can you guys hear me?
Yes,
Yeah.
we can.
Yeah.
Okay, great.
Wow, what the heck?
Thanks, guys. So let's see, where was I? Sorry, my internet is just awful at home, and I think it just went down. And I'm using my hotspot, but I'm writing on my iPad. That's why that didn't go away. You just lost my charming looks and wonderful voice. Okay, so I should just remember to do the hotspot. So sorry about that. Okay.
Professor,
Yes.
the iPad is still recording the whole lecture, correct?
Actually, the iPad is not recording. This is another tricky thing. This is why I'm doing this complex thing, is because that's a long story short. Zoom only records locally on the Mac or PC, and the iPad, and only records on the cloud, and the recording time's limited on the cloud. So what I'm doing, that's why I have like a laptop that's logged in and recording, and then on iPad, I'm also joining the same meeting and sharing my screen. So
Okay.
So
Wanna
so what we'll end up with is 2 videos, one before and one now, and I'll splice them together, and hopefully, I'm hoping it'll appear. I mean, there'll be kind of a disjunction between them, but I'm hoping it'll look like one video.
Okay, thank you. Just wanted to make sure things were going to be fine.
Yeah, I'm not 100% sure myself, but that's the idea. Let's hope. Sorry, it's just all these limitations and things. Maybe they fixed it by now. I should double check. Anyhow, sorry about that. I'll just try to remember to do the hotspot thing from now on. Okay, so where were we? Okay, so we were talking about the velocity of the holes and the velocity of the electrons as a function is related to the electric field, but with this proportionality constant called the mobility. And it turns out in silicon, the mobility of electrons is much higher than the mobility of holes. So by a factor of 2 or 3. It depends on honestly depends on the doping concentration, the material, but it's always kind of around the case. Okay, it depends on the temperature and a whole bunch of other stuff. But that's only important later on, I think, as we'll see. There are 2 types of MOS transistors. One of them has electrons that are flowing through its channel, and the other one has holes flowing through its channel. The one with the electrons called an NMOS, the one with the holes called a PMOS, and just that the NMOS currents for the same device sizes, et cetera, are like 2 or 3 times higher than the PMOS currents. But anyway, so this is just sort of some background info here. But the main thing to get out of this is that there is a current mechanism in semiconductors that is a function of the electric field across the semiconductor. And it's the current is moving in the direction of that electric field or an opposite direction to the electric field. It depends on whether you're talking about electrons or holes. And what else do I want to say about that? And as a function of the electric field. So that's one current. And then there's a the mobility of the carriers in that material determine or sort of gives you how much current you'll end up with. Okay, so that's probably saying too much. A picture is worth 1,000 words. So let's now look at, so we have this case where these carriers are moving through with the electric field. So now we want to figure out, well, okay, what is the current here, right? So if we look at the current, we can say that if you have a certain velocity, okay, and so the velocity we get from this equation, or this equation depends on whether you're looking at electrons or holes. And then you look at a certain volume. So the certain volume is this width, this height, and width, height. No, what am I saying? Sorry, it's just the width and the height. Okay, so it's not a volume, but a sort of a square like that. Okay, and so the current is the velocity and the width and the height times the number of electrons times Q is the charge of an electron. So Q, you'll see that a lot in this class. So Q is charge of electron. It's 1.6 times 10 to the minus 19 coulomb, which is one of the few numbers I actually remember. Okay, so that ends up being your current. And you know, this is derived in the book. I wasn't going to drive it because it's, you know, really I'm only interested, again, I'm trying to move quickly through this stuff so we don't get bogged down. I'm only really interested in the final thing here, which is then if you look at the current density, so because this volume is WH times L is this volume. So if you want to get the current density, we'll end up with this. We basically take that current, divide by that, and end up with mobility times the electric field times the carrier concentration for electrons times the charge for an electron. So that's the current density of electrons, okay, in the semiconductor. But we also have holes in the same semiconductor. So they have also a drift current. So this is the electron drift current. And so because of the holes, you also have this hole drift current, okay, which is just the mobility of the holes times the electric field times the density of holes times the charge of an electron, okay, which is the negative charge of a hole, I guess, is one way to look at it, okay? So in total, this is your drift current density, okay? And basically, what does this say? It says basically that the electrons and holes carriers, because they're charged differently, but then they react differently to the electric field, they're basically adding with each other. So you end up with electron drift current and a hole drift current, and you add them together basically. And any questions about that? So that's drift current, and it's one of the two types of current in a semiconductor. Okay. And this is just some housekeeping stuff. And what it says is, you know, if you look at this equation, it seems to imply that as the electric field goes higher and higher, the velocity goes higher and higher of electrons or holes. But it turns out that the velocity actually saturates. So that equation, the simplified equation, seems to imply that you'll have some kind of a equation like this, with this slope being given as the mobility. But in reality, you have this sort of critical electric field, and the mobility basically saturates. But again, this is just housekeeping for your background. You just need to know the mobility. Okay, so drift current, it goes in the direction of the electric field. If there is no electric field or no potential across the semiconductor, there's also no drift current. Okay, and the second type of current transport in semiconductors that does not exist in conductors is called diffusion. And diffusion is, you know, the calculations, I got wrapped around the axle every time I think about this, but it really just comes from derivation of the Brownian motion of particles, any kind of particle, electrons, holes, whatever, or, you know, like ink in a glass of water or something. So basically things generally move, I mean, not generally, always move from a place of high density to a place of low density. So if you have if you drop a drop of ink in a glass of water, eventually, initially right around the drop is where all the ink is at, all the colored pigmentation. But eventually those colored pigments will get to all the, wherever there is less color pigmentation in the water. So, and then they'll just sort of diffuse and you get a uniform concentration. Okay. And so the same thing is true in a semiconductor. Is, let's say you have a piece of semiconductor and somehow, and we'll see how, somehow you magically end up with you end up injecting a bunch of carriers on one side of this thing. So you have an excess amount of carriers there. Even if there is no electric field, just because there is less carriers here than here, the carriers tend to move from a place of high carrier concentration to a direction of low carrier concentration, just because there's fewer of them on that side. Okay. And this is basically,
So, Professor, it's kind of like gravity, like going from a high point to a lower point, kind of like that.
I tend to think of gravity as more like the drift, because the gravitational waves are giving a certain direction for something that has mass, that's pulling it towards the place of high gravity. This is more as if there was no Earth, say, and you were in space somehow without gravity, and somehow magically you put a bunch of things, a bunch of pieces of stuff in somewhere in that space without any gravity. They'll just diffuse out to fill that space uniformly. Does that make sense? Because gravity is, if you think about it, is directional. If you have a heavy object is pulling stuff, and if you look at, the gravitational pull, it's pulling it towards the center of that massive object or anything that has mass. So it's more like the drift rather than the diffusion. This doesn't, the diffusion mechanism doesn't need any push from any other external fields. It just, because you have a higher concentration and a lower concentration, things diffuse out. And there's also, because there's no external push, there's no, it's sort of unitary. It just goes from high concentration to low concentration. So if instead of this drawing, we had like a, a cube, and somehow we had a excess of charge carriers or any kind of thing, mobile object in the center, it would really drift radially equally in all directions from high concentration to low concentration. So, and it's just a difference in concentration.
Professor,
Oh,
so
okay.
just so that I know, so it'll diffuse until it reaches a point of equilibrium, right?
It'll diffuse till it reaches a point of equilibrium. Yes.
Thank you.
Yes. Which will be another point of interest in a bit. So, okay. So, but keep that, that's an important point. So, okay. So let's say, so drift and diffusion. The only thing you need to know, again, sorry to be a broken record here, but let's beat this thing to death. Drift is a function of the electric field. It's the direction is set by the electric field. If there is no electric field, there is no drift. Diffusion, all that matters is there's a difference in carrier concentration. And somehow magically, in this example, we are dumping carriers on this side of this box or cube or whatever it is. It's not a cube, whatever, what is the structure? Rectangular cube, whatever. And they're diffusing in this way. And it'll become clear why we picked this shape. But then the other thought experiment, again, you're gonna have to trust me about how this happens, is let's say we actually dumped the carriers somehow in the middle of this thing. And now they will again go, these guys will, some of them will go in this direction, some will go in this direction because you have a lack of carriers both here and here. So they'll go in both directions to fill those areas with more carriers. Okay? That'll become clear why. Just sort of right now, just keep that in your head. Okay, so basically what we're saying here, I put a little note down here to remind myself. So now we looked at drift. We came up with this current equation and current density. Now I want to do the same thing for diffusion. And the first thing that we kind of notice about diffusion is we're saying that the current, if the current is being caused by these charged carriers going from low concentration to high concentration, from high concentration to low concentration, so the current must be a function of the change in carrier concentration as a function of distance, say in this case. Okay. As a thought experiment. So basically what you end up with, and because, you know, we're talking about, there's a certain area, so the current is also a function of the area. And because there's, you know, a charge associated with an electron, we throw that in there as well. So we think there's disproportionality of the current. And it's indeed the case. So we have this proportionality current to these three factors, the area, the charge of an electron, and the change in carrier concentration as a function of distance. And the proportionality constant is this d sub n, which is, its name as diffusion constant. And it's also a function of, you know, this thing being silicon, and it's different for electrons and holes. So the electrons have a certain diffusion constant, the holes have a certain diffusion constant. Okay. Now, the interesting thing is in the drift, because the electrons and holes were, you know, electrons are negative, holes are positive, so they're reacting to the electric field in opposite direction. But then because they're charged differently, you have to add that to it. So those two cancel out, and you end up with the electron and hole drift currents adding together. Okay? But in the case of diffusion, because there is no electric field, just carriers are going from high concentration to low concentration, the only thing you're left with is the difference between one being negatively charged and the other one being positively charged. So what you end up with in the case of diffusion current is they subtract from each other. Okay, so the electron and hole diffusion currents are actually subtracting from each other, whereas the drift currents were adding to each other. Okay. All right. Well, I think I'm going to jump. We don't have time. We're doing okay. well, maybe we'll just talk, this is just a couple of examples, but maybe this one's the easiest one to think about. So all it's doing is, it's saying that in the case where you have a uniform charge profile, okay, the change in the dn, the change in n with respect to x here for this guy is just n divided by L, and minus n divided by L. So in the case where you have a uniform change in distribution, you just plug in n over L, which is the slope of this uniform line, and you end up with minus q dn n over L. So in this region, that in this particular example, that's the carrier, that's the current density, okay? And in the case where you have an exponential relationship, the change in carrier concentration respect to x, because it's an exponential distribution, ends up being this derivative of this exponential and looks like this guy, okay? Which is just taking the derivative of the exponential. Okay, now both of these end up being somewhat useful too, but just sort of keep that in mind as we'll drive more. Okay. All right. And then lastly, this is really, I don't think we're gonna, well, so for some reason, which I won't get into, I'm not sure I fully understand myself, although, we said the drift current is a function of electric field, okay? And the diffusion current is just a function of the change in carrier density. So they're really two completely different physical things, phenomena. We're not driving one from the other. You'll get the diffusion even if you didn't have charged particles. So they're just completely different. But still, the diffusion constant, D, is related to mobility with this proportionality factor. Maybe it's a message for humanity, I don't know, which is the Boltzmann constant times temperature over the charge of an electron. So D over mu is another one of those equations that I remember, one of the few equations. D, which is D is a diffusion constant that was used in the diffusion current, and mu is the mobility that was used in the drift current. That proportionality is the Boltzmann constant, which is a constant, times the temperature over the charge of an electron. Okay. Ooh, how interesting. Well, the reason I mention this is because this factor, KT, oh, whoops, am I erasing stuff? Because I keep getting jumping over. This KT over Q will show up in our current equations, okay? And a really good number to remember is KT over Q at room temperature. Okay, so at 300 degrees, KT over Q at T is equal to 300 degrees is approximately equal to 26 millivolts. So remember that because it'll just keep showing up. Otherwise, you're going to have to keep multiplying the Boltzmann constant, which is an awkward number, by the temperature divided by the charge of an electron, which is another awkward number, and it'll just, instead you just remember as 26 millivolts. Okay, so, all right. Any questions about that? So far, just sort of keep that in your heads. Hopefully in the next set of slides, which are coming along, we'll see how these things sort of all fit together. And we're trying to fit all this stuff together to see what happens when we build our first device, our first semiconductor device. Okay. All right. Okay. So let's see. Now I gotta.
So Professor, just
Yeah.
the temperature is in kelvins or Celsius?
Yeah, the temperature is always in kelvins in this class. Yeah, and all these equations always use kelvins in all semiconductor equations. Let's see. All right. Okay, guys, so this was the last slide where we left off. Okay, so now with all that, we're going to build our first device, which is a diode. Okay, you may have heard about diodes in the lab classes or something. You've almost certainly heard about light emitting diodes, LEDs, which are in your TVs or some laptop screens, etc. Those are diodes that if you put a current across them, they'll emit light, but they're diodes nevertheless. But anyway, so it's a diode is a, we'll sort of get into the usefulness of a diode and how to treat it as a circuit element like we treat a resistor or capacitor, although it's a nonlinear circuit element, and you can do a more interesting thing about it. But so let's talk about how you build a diode. And you basically, the way you build a diode is by butting up an N-type material next to a P-type material. Okay, so this material is N-doped, so it's got a bunch of phosphorus. And then this side, the P side, has got a bunch of boron. Okay, and the way you actually do this is you really have one piece of silicon, and you bombard this side with phosphorus. You put a mask here, bombard this side with phosphorus, or actually all sides, but this mask stops the phosphorus from getting into this side. And then you basically, after that, you cover up this side and you bombard the whole thing with boron. And so you end up with a bunch of boron on this side and a bunch of phosphorus on this side. So you'll get basically this NP junction. Now the N-type material, just butt it up right up against a P-type material. And that, the electric symbol, so in the schematic, you won't be drawing this box. You'll be drawing this symbol, okay?
Very glad I cannot draw boxes. Thank you.
I'm sorry?
I'm not very good at drawing boxes, so I'm glad.
Yeah. Yeah, so we're gonna, I'm hoping to get through this. You just need to know this stuff for the background, but we want to move, this class is for circuit designers, okay? That's our goal here, is to learn how to do circuit design with these material. So this is just background stuff to get us to that level. So this is the diode, and this is all, the way you draw it is a convention. And by convention, this side with this bar, this side is called the cathode. And this side, on this other side of the rectangle, is called an anode. Don't know why. I think it had something to do with vacuum tubes. Maybe they were called cathode and anode. Honestly, I still have to look this darn thing up every once in a while because I get confused which side is called cathode and which side called anode. But the thing I will not forget is that this side, the cathode side, I always think of it in terms of the symbol, is N-type doped, and the anode is the P-type doped side. Okay. Okay, so what we're gonna then, so going forward for the next few slides, what we're gonna talk about is what does this structure look like, and how do we calculate what happens in terms of a current in the structure and in terms of a capacitance of the structure. So this structure has some interesting properties, both if you plot. So I'm going to give you guys a spoiler here. Spoiler alert. So if I plot the voltage So let's say this is my, I'm gonna plot, or should I plot this? Okay, let's say I take my diode. I plot it like this. I hook it up to my voltage source like this. Okay, so my voltage supply, the plus side is connected to the p-type material or the anode. The minus side is hooked up to the cathode. Okay, so as V goes up, as this side goes up in potential, this guy, your current goes up very quickly, exponentially, very, very quickly. Okay, and as this voltage goes down, so it goes negative, you get basically kind of a flat curve with voltage. So like a resistor, remember a resistor, this is like kind of more interesting from a resistor is because a resistor just does something like that, right? Nothing, it's not asymmetric. So we'll see how this is like very, very useful. Although resistors are useful too, God knows. But anyway, so it turns out that you can use this as a switch because it conducts in one direction and not in the other. You can use it as a switch that turns on when the voltage is has a certain polarity and turns off when the polarity is reversed. So, which isn't the case in resistors, like, you know, they conduct both. So that becomes very useful. So that's the current. The other thing that this device does is it has a capacitance that's in series with it. So it has this current times voltage characteristics. But then if you look at the voltage versus capacitance of this guy, it also has a very interesting characteristic that as the voltage across it goes in, when the voltage is negative, as the voltage across it goes down, as the voltage across it goes down in this direction, the capacitance goes up. And then the capacitance goes down as the voltage across it goes, gets high, okay? Over here, you don't think of it as having a capacitance because over here, we sort of see it as an on switch. So there's no, you know, it just looks like a resistor here or like a conductor. So it won't have any series capacitance. So it's only when it's not conducting here that you see this capacitance. So this capacitance is very interesting because you have a voltage controlled capacitor, and it turns out that you can use that if you want an oscillator. So let's say, remember we were talking about you have this oscillator in your cell phone that creates the carrier frequency, and you put your voice signal on top of that carrier frequency. If you want to modulate, change the frequency of that carrier, you can use a diode and you can change the voltage across the diode to get different frequencies. So it's so that's primarily where having a voltage controlled capacitor is useful. Now a regular capacitor, it has the same capacitance regardless of the voltage across it. It has the same capacitance, it'll have a different charge, but same capacitance. This one actually changes its capacitance with the voltage across it, which gives us some interesting things. So you get those two guys. Okay. So let's get thinking about how. So we need to take a few steps here to figure out how to get the current. So that's the first thing we're going to do. Or is it to get the? Well, I don't know. Maybe we'll do the capacitance first. We'll see where life takes us. But as a first step, we have this N-type material on one side and P-type material on the other in our PN junction. Okay, so if we just look at this N side, it has, remember we talked about majority carriers and minority carriers. On this N side, the majority carriers are electrons. So they say, so they call that N, which is the electrons, sub N, because it says the electrons in the N side of this PN junction. Okay, this is the PN junction. And on the N side, you have N, which is the electron density of N, which is the N side of the junction. On the P side, the electrons are minority carriers. Remember, again, going back to the previous set of slides, in a P-type material, the electrons are minority carriers. So we call that N sub P implies electron density in the P side. And same inversely with the holes. So in a P side, P-type material, the holes are the majority carriers, okay? So, and then we specify that by P sub P, which means the holes on the P side. And then in the N-type material, the holes are the minority carriers. So you have P sub N, okay? So, and then because you can't have you need sort of a smooth transition. So this is on this side of the N, on the extreme edge of the N, that's the case. And on the extreme edge of the P, that's the case. But at the junction, as you're transitioning, somehow you got to transition between here and here. And so we've drawn something that we're going to get more into the details of here. So this rough curve that takes you from one side to the other, and a corresponding curve for the holes going from one side to the other. What that means is that here, like around this area, we need to figure out what the electron and hole concentrations are in that area. And that's kind of an interesting thing that we're trying to figure out. Any questions about that?
So basically, we're just applying the diffusion principle where since on one side we have more electrons and on the other side we have more holes, they just migrate to the other sides, right?
That's correct. In the absence of electric field. That's what they're going to do.
Okay, thank you.
Sure. Okay, but before doing that, let's do an example. So let's say we have, I'll give you guys maybe like a few, I don't know, five minutes to give a shot at this. This is actually example 2.11 in the book. It says, okay, we have a PN junction and we have well, let me draw it the same way I did here. So the P-type, the acceptor concentration is N sub A, and that is 1 times 10 to the 16th per centimeter cubed. And so, and the N side, the donor concentration is 5 times 10 to the 15th per centimeter cubed, okay? And then it wants to know the electron and hole concentrations on either side here. So remember, on the N side, you have an electron concentration on the N side and a hole concentration on the N side. And on the P side, you have, sorry guys, on the P side, you have a P carrier, P concentration, the hole concentration on the P side, and an electron concentration on the P side. Okay, so we want to figure out these 4 things. So why don't you guys give it a shot at it? About 5 minutes.
And are we assuming this is silicon?
Yeah, I'm sorry. We're assuming it's silicon, and we're assuming it's room temperature.
Thank you.
Sure. Okay, guys, let's walk through this thing. So, so firstly, we're looking at the concentration of electrons on the n side. And remember there, because these are majority carriers, so this is approximately equal to n sub d, or the donor concentration. So it's equal to 5 times 10 to the 15th per centimeter cubed. Okay. And when we look at the whole concentration on the P side, again, their holes are the majority carriers, and they are approximately equal to the acceptor concentration. And that is 1 times 10 to the 16th per centimeter cubed. Okay. And then remember the equation that n, this is a general thing for everything, n sub p is ni squared. Okay, this is always true, but you got to remember the intrinsic carrier concentration is a function of temperature. Okay, but anyway, at a given temperature, if you have the n concentration, you can get the P. So P sub n is ni squared over n sub n. So is equal to ni squared over n sub d. Okay. And then remember, this is ni at room temperature at T is equal to 300 K is 1.08 times 10 to the 10th per centimeter cubed. So this is 1.08 times 10 to the 10th squared over 5 times 10 to the 15th. Which is, I don't know, see what the book says. I think it's saying it's 2 times 10 to the 4th per centimeter cubed. And same with this. And so P on the whole side, on the P side, the electrons are the minority carriers. So that's equal to Ni squared over P sub P. So it's 1.08 times 10 to the 10th squared 1 over 6 over. So the P sub P is N sub A. This guy. So that's 1 times 10 to the 16th, 1 over centimeter cubed is equal to 1.0. Nope, 1.1 says 1.1 times 10 to the 4th centimeter cubed. Okay, so anyway, that's the example. Now the interesting thing I like about the example is it gives you some actual sort of numbers. So look at the N side. On the N side, the electron concentration is sort of in the 10 to the 15th type of number, 5 times 10 to the 15th. And the whole carrier concentration is in the 10 to the 4th. So 11 orders of magnitude lower than the electron concentration. So you can kind of get a feel for the difference of concentrations between the majority carriers and the minority carriers. It's a huge difference. And same on the P side. On the P side, the acceptor, the whole carrier concentration is 1 times 10 to the 16th per centimeter cubed, and the electron carrier concentration is 1 times 10 to the 4th per centimeter cubed. So that's 12 order of magnitude, 12 orders of magnitude difference between the whole concentration and the electron concentration. It's just kind of interesting to see so there's a huge difference between the majority carrier and minority carrier concentrations. Okay, guys, I'm going to stop here. And so, any questions?
Professor?
Yeah.
I had a question about how'd you get the Ni value? I'm not sure if I missed it or something, but.
Sure. So the Ni value, we got it going back to this equation here from the previous set of slides. And like I mentioned, this is a good number to remember, 1.08 times 10 to the 10th for Ni at 300 degrees. But if you were gonna come up with some other funky temperature, then you'd have to do this whole calculation of Ni using this equation. And I think actually one of the homework problems, so you have to do that. So, you know, you stick it in an Excel sheet and change the temperature. And here, basically, all you need to know is the band gap of silicon and the Boltzmann constant. Does that answer your question?
Yeah, thank you.
Yeah, just it's really handy that, you know, 1.08 times 10 to the 10th or 1 times 10 to the 10th at room temperature per centimeter cubed. It's a handy number to remember. But, you know, yeah. I was going to say I'd give it to you guys, but I'm not sure I will in all cases.
Professor?
Yeah.
Just to clarify, intrinsic semiconductors and eccentrics, the main difference is one is doped and one isn't, right?
Yeah, yeah, The intrinsic semiconductor is completely undoped. So, let's say you take a silicon. Intrinsic silicon is just silicon. So just silicon, the concentration of electrons and the concentration of holes is exactly the same because every time you create an electron, you create a hole because a hole is a lack of an electron, okay? So that's intrinsic silicon or intrinsic semiconductor. When you have a doped silicon or doped semiconductor, because you have injected these dopants that have a different characteristic, they have a different number of valence electrons, then they don't have, every electron does not necessarily have or does not have a corresponding hole because you just get this excess of electrons. Every time you implant, if you take a centimeter cube, every time you implant a phosphorus atom in there, you end up with one additional electron compared to a hole. Okay, because each one of those has one extra valence electrons. And so if you implant 1 times 10 to the 15 phosphorus atoms in that centimeter cubed, you end up with donor concentration, electron concentration, excess electron concentration of 1 times 10 to the 15. And for a p-type material, same thing, because you have a lack of the valence electron, if you implant boron into that silicon, for every boron atom, you get an extra hole. Does that make sense?
Mm-hmm. And so they have to be together in order to do the drift, correct? The donors and the acceptors have to be together to have the drift.
No, you can get, so let's say you just had a piece of silicon that just had donors, okay? If you put an electric field across it, you'll get a current that basically has the majority carriers going in one direction and the minority carriers going in the other direction, and those two currents add. So you don't need to have an NP junction to have drift current. You just need a piece of silicon. In fact, even if you had an intrinsic piece of silicon, if you put an electric field across it, you'll get a current going across it but the current will be the same for the electron and the holes because there's no majority or minority carrier. They're exactly the same.
Also, we're just doing it for the change in density.
Yeah, it's more subtle than that. So when you put a PN junction together, you'll see the subtlety of what the drift and the diffusion current. It's not as, the drift current's always there if you had just one chunk of material with an electric field or a voltage across it. But when you put this PN junction, you get a funky interaction, and you'll see what it is. It's not as straightforward as you think. Otherwise, you'll end up with like a resistor. If you just had an N, or just had a P, or just had an intrinsic, and you put an electric field across it to get a current, you'll just get a resistor going one way or another. But if you get a PN junction, you get this asymmetric type of performance, like I mentioned with the diode. In one direction, it's different than the other direction. And it's kind of a subtle interaction. You'll see how it pans out. It's not a straightforward thing that you can just imagine how it will work. We'll see it in the next lecture.
Okay.
Thank you, Professor. Appreciate it.
Okay, thanks guys.
Have a great weekend.
Have a good weekend.
Professor.
Thank you.
Thanks, bye.
Wait, Professor?
Yeah,
I have a question.
sure.
On the transportation mechanism drift slide, I think there was something, I don't know if I'm thinking wrong, but there might be something off with the math.
Okay, there sometimes is, can you tell me which number?
I didn't write down the slide, but it had like the box with the arrows drifting towards the right.
Are you talking about this one?
Yes.
Okay.
Because the integral has the limits from b to a, but
Yeah.
it's a negative integral. So wouldn't that just cancel out the negative sign?
Yeah, you know, this is kind of funny. So, you know, actually the electrons are going in this direction, but let's see, electrons are going that direction. So let's say if the electric field is, shoot, you know what? Is this Aaron asking?
Yes.
Hi, Aaron. Can you email me that? I got a class right after this one. I got to prep it. I need to like sort of work out the integral for you. So if you just remind me of your question, I'll do that and put it up next class.
All right. Sure. Sounds good. Thank you.
Awesome. Thank you, Aaron. Appreciate it.
Thank you, Professor.
Thanks. Take care.